Hello and welcome back to e-sipnayan. For today's video, we are going to discuss how to graph piecewise functions. But before we proceed, do not forget to hit like and subscribe so that you'll get notified once we upload new videos. Here are the learning objectives that hopefully we are going to achieve at the end of this video. First, you should be able to identify the characteristics of a piecewise function. You should also be able to graph a piecewise function, evaluate piecewise functions, and lastly, solve word problems involving piecewise functions. We now start by defining what a piecewise function is. And piecewise function is simply defined as a function that combines pieces of different functions. Or in other words, when we say piecewise functions, it's just a combination of functions, and at least two functions. So we already discussed two different types of functions, namely constant and linear function. So when we discuss now piecewise function, it can be a combination of constant and linear, both constant or both linear. Let me present the equation on how you're going to write a piecewise function. Of course, f of x here is the symbol denoting a function. And we have here a grouping symbol which states that the function refers to two different functions. Usually, the functions are written in rows. The first row given this piecewise function represents a constant function. How do I know? Because in this part of the piecewise function, this is where we are writing the functions. So basically, for it to become a piecewise function, we have to have at least two functions. For this portion of the piecewise function, this is the one assigned or allotted to write the restrictions. This is simply the domain of each function. When we say domain, these are the values we can substitute to the value of x given the function. So basically, this is the format in writing a piecewise function. We have the function f of x, we have a grouping symbol, and we have at least two functions. Moving on, let's have this example to explain further. So f of x here pertains to the symbol of function. We know that we can also write it as a variable y. Meanwhile, this grouping symbol here is very important because it represents that we are grouping different functions. Moving on, this portion of the piecewise function is the one allotted to write the functions. In this case, we have 2, negative x plus 2, and 3x minus 3. So this piecewise function contains two functions that are both linear. Then this portion of the first row, if x is less than 0, it pertains to the domain of the function aligned to it, which is negative x plus 2. Meanwhile, x greater than 0 is the domain of, again, the function aligned to it, which is 3x minus 3. Just a little reminder, when we say domain, we are simply pertaining to the possible values of x which we can substitute to the given function. The restrictions are very important because it will help us determine the only possible values of x we can substitute. So for the first function, negative x plus 2, since our restriction or the domain here represents that x should be less than 0, that simply means that we can only substitute the values of x which are less than 0 to the given function negative x plus 2. So some examples are the negative numbers. Meanwhile, for the second function, the domain is now x greater than 0, meaning we can only substitute the values of x that are greater than 0 to the given function 3x minus 3. Some examples of those numbers are the positive numbers 1, 2, 3, and so on. Let's now discuss how to evaluate piecewise function. And in evaluating piecewise function, it's the same as mere substitution. Now, say for example, we are tasked to evaluate p of 2, and we know that 2 here is the one to be substituted with w. But since we have three functions, we need to identify which among them are we going to use. Now, we answer this question. 2 falls within which given domain. So in the piecewise function, we have three domains. Let me label them as A, B, C. So the first domain is W is less than or equal to 15. The second domain as B. And lastly, C, W is greater than or equal to 40. Now we select which among here we found 2. And by analyzing, we can say that 2 falls within the first domain, which is W is less than or equal to 15, because definitely the inequality will become satisfied. It is indeed true that 2 is less than or equal to 15. Now, after identifying which domain 2 falls, we now substitute 2 to the first function, because the first function is the one containing the correct domain. W is less than or equal to 15. And the first function is a constant function, meaning no matter what we substitute to a constant function, the value will not change. Hence, when we evaluate P of 2, the result will still be 100. So when we want to evaluate P of 2, that's the process. And this is now the value when P is 2. Let's have the same piecewise function, but this time substitute a different value. Say, for example, this time we will be tasked to evaluate P of 25, where 25 is the one you're going to substitute as W. So again, we ask this question, 25 falls within which domain? So again, we label the three given domain as A, B, and C. Let me just do it again. So the first one is W less than or equal to 15. That's the second one, labeled as B. And the last one is W greater than or equal to 40. Now, analyzing the three given domain, we choose B because definitely the value of W to be substituted, which is 25, is greater than 15 but less than 40. So when we write or substitute 25 as W, the inequality will be satisfied because basically 25 is indeed greater than 15 but less than 40. Hence, the inequality is satisfied. Now, after checking which domain are we going to use, next task is to substitute the value of W, which is 25, to this time the second function because we used the second domain. The second function is again another constant function. So whatever value we substitute, it will be the same. So if we want to get P of 25, the result is still 200. Let's now have another example. We are tasked here to evaluate P of 10, where 10 here pertains to D. So again, we analyze the given domain and we know that D greater than 4 is the one that will satisfy the value of 10 given the inequality, because 10 is definitely greater than 4. The next step is to substitute, and where are we going to substitute 10? To the function on the given second row. So basically, we let D be equal to 10, given the second function 8 plus 1.4 quantity D minus 4. The next few steps are just mere substitution. So copy 8 plus 1.4. We let D be equal to 10. Afterwards, we subtract with 4. Next step is to simplify the equation. That will be 8 plus 1.4 times 10 minus 4 is 6. Then that will be 8 plus 8.4. The sum is 16.4. Hence, if we evaluate P of 10, the value or the result is 16.4. And that is now our final answer. Let's now discuss how to graph piecewise function. But before that, let us recall something about inequalities. First question, what inequality symbol is used for an unshaded circle? The answer is less than or equal. Next, in graphing a restriction, what symbol is used for a shaded circle? That is less than or equal or greater than or equal. So why do we need to recall whether the given inequality will be graphed as shaded or non-shaded? You know very well that in a piecewise function, we are given with the restriction on the domain. And usually, these given restrictions are in terms of inequalities. So basically, it's very important that you know how to graph using inequalities. Let's have the first example. So we have here the given piecewise function consisting of a constant function and a linear function. These are the given restrictions. For the first constant function, the domain is that x is less than or equal to 1. For the second function, x is greater than 1. So how do we graph this one? First, we need to graph the functions individually. We're going to graph first f of x equals 5. So how do we graph this? It will be somewhere here because y equals 5 is above the origin, and then you simply draw a horizontal line. Next, we need to restrict the domain. And again, when we want to restrict the domain, we simply want to cut the graph in such a way that the values encompassed by the horizontal line will be satisfying this inequality wherein x is less than or equal to 1. Now you think, what are the values of x less than or equal to 1? Basically, you start with 1, 0, and the negative numbers. So, since this is an inequality symbol less than or greater than, we are going to use a shaded circle. So, we are going to plot where x equals 1 is aligned along the x-axis and the given horizontal line. Then, after that, we're simply going to cut our horizontal line so that the values along the x-axis that it will encompass will be from 1 and everything less than 1, which are the negative numbers. And then again, we use here a shaded circle. So that is how we are restricting the graph for a constant function. Next, we are going to graph now the second function, which is a linear function 5 minus x. And here, I want to graph this linear function using the rise and run or the slope-intercept form. Now, our slope here is negative 1 over 1 because the coefficient of x is negative 1. And for all whole numbers, will have an automatic denominator of 1. So meaning, since the numerator is negative for the rise part, we're going to move downwards only 1 unit because negative 1. And then for the denominator, since it is positive, we're going to move to the right 1. We are going to plot the first point, which is at 0, 5 because B is the y-intercept. So it is at this point. Then after which we now apply the rise over run to get the second point. So we are going to move 1 unit downwards, then 1 unit to the right. Then afterwards, we plot the next point. After which, we can now draw the line. And this is now the red line representing 5 minus x. Now, since we have here a restriction on the domain, we only want the line to encompass values along the x-axis greater than 1. So definitely, 1 is not included. What are now the values greater than 1? So that will be 2, 3, 4, and so on. So let's just plot along this line where is the value greater than 1. That will be 2 and everything to the right. But since the inequality symbol is greater than, we will be using an unshaded or an open circle. And we will be plotting it exactly aligned to 1. So if this is positive 1, we just align it to the graph. And we are going to put the open circle or unshaded circle here. Then afterwards, since we only want values greater than 1, we want to check which part of the graph are we going to eliminate. Is this the part from this point going upwards, or is it the part from this point going downwards? The answer is this portion going upwards because all values that encompasses this line going upwards will be values from 1 and everything less than 1 because it is going to the left. So what's left now will be from this point at 1. Okay, we are now going to retain the graph going to the right. And this is now the graph of the piecewise function 5 if x is less than or equal to 1 and 5 minus x if x is greater than 1. And that's one example on how you're going to graph a piecewise function. Next, let's have some more practice. Let us graph the given piecewise function. So we have here x if x is greater than or equal to 0, and negative x if x is less than or equal to 0. Now let's first graph f of x equals x. That will be a slope, and the slope will be 1 over 1. So meaning we're going to move 1 unit above and 1 unit to the right. Now to plot the first point, we plot the y-intercept. The y-intercept is exactly along the x-axis. So that's the first point. To plot the second point, we use rise over run. So move 1 unit above from the origin, then 1 unit to the right. Then plot the second point here at 1, 1. Connect the lines, and the yellow line is now the graph of f of x equals x. Now, if we want to restrict the domain in such a way that it will just be greater than or equal to 0, let's draw a shaded circle on 0 because the inequality symbol greater than or equal represents a shaded circle. Then we analyze what values do we want. The one going downwards this line from the origin, or from the point of origin going upwards. Remember that we want the value to be greater than 0. And the values greater than 0 that the graph will encompass will be to the right of the origin, or this portion of the graph going upwards. So we are now going to omit or delete this portion of the graph going downwards. Now this ray is the graph of f of x. Given the restriction, x should be greater than or equal to 0. Moving on, let's try to graph negative x. Same procedure. So we plot first the y-intercept exactly at the origin. This time, the movement to plot the second point will be 1 unit downward and then to the right. So from the origin, move 1 unit downward and 1 unit to the right. We're going to plot the second point at 1, negative 1. Then connect the points to form a line, and the green line now is the graph of negative x. But take note that we have a restriction and we want to graph only when x is less than or equal to 0. Again, we are going to use here a shaded circle because the inequality is less than or equal. So that is exactly at the origin. And then we choose the graph we wish to eliminate to satisfy the restriction. And since we want values less than 0, that will be the portion of the graph going upwards, starting from the origin. Because those are negative 1, negative 2, up to negative infinity. To the right of our point will be positive values, which we do not want for our restriction. Hence, we omit that part, and we will be left with this given equation. This is now the graph of the piecewise function x if x is greater than or equal to 0, and negative x if x is less than or equal to 0. And that is all for this video. See you on the next one. Bye!